All right, let's work some example problems on concentration of solutions. Specifically, in this chapter, we're talking about aqueous solutions. And so we learned some of the fundamentals of the idea of concentration, specifically in relation to solutions to where the solvent is a liquid. There's all sorts of different kinds of solutions. You have solid solutions, like steel is a solid solution of carbon and iron, in a lot of cases with different alloys of steel. There's other solutes other than carbon. But right now in chapter 4, we're just getting introduced to the idea of concentration with respect to aqueous solutions, which are solutions where the solvent is a liquid and is water. Okay, so write the equation for calculating molarity. Why is molarity a convenient concentration unit in chemistry? Okay, so what we learned in this chapter is that the purpose of concentration, this property of concentration, is you have a concentration of you're referring to the concentration of a specific solute in a solution, right? A homogeneous mixture, you can also call a solution. A solution is another name for a homogeneous mixture, and with homogeneous mixtures, that's when the terminology of solute and solvent come into play. There can only be one solvent in a homogeneous mixture, the component that's present in the largest amount, but there can be multiple solutes, one or more solutes. And with concentration, you're referring to the concentration of a specific solute in a solution. And the purpose of this definition of this term concentration is it allows us to quantify the amount of different substances in a solution, right? Because we need to do stoichiometry, for example, on reactions in solution. With stoichiometry, you need to be tracking the amounts, whether it be in terms of moles or grams, in any amount of the different compounds. Well, if we're in solution, the way we describe amounts of substances in the solution is with respect to the concentration of the different substances or solutes in the solution. Okay, now there's many different ways that you can express the concentration of a substance in a solution. And we're going to learn about a lot of these ways in chapter 12. But here in chapter 4, we learned about the most commonly used unit for expressing concentration, which is molarity. The molarity of a specific solute in a solution, and we're thinking about, at the moment, solutions to where the solvent is a liquid, is the number of moles of that solute in the solution divided by the volume of the solution in liters. So the molarity of a specific solute in water, for example, if you're going to dissolve, let's say, some salt, some sodium chloride in water, and you want to state what the concentration of the sodium chloride is in the resulting solution, then you're going to want to determine how many moles of NaCl did you add to the solution, and then divide that by the entire volume of the resulting solution in liters. And you're going to get, the result is you're going to have a certain number of moles of sodium chloride per liter of solution. Now, there's a couple things to note here. One is that you might see definitions of molarity referred to as the moles of a solute per liters of solvent, instead of saying liters of the solution. And the reason why the definition is being stated this way is because in the majority of cases, the difference in volume between the pure solvent, liquid solvent, and then the resulting solution after the solute is dissolved is negligible. Okay, but technically, if you want it to be extremely precise for whatever reason, if you want to know the precise definition of molarity, it's, you could have multiple solutes dissolved, potentially, right? But it's whatever the final solution is, the final solution with all the solutes dissolved is going to have a certain volume. That's the volume that goes in the denominator here. And then in the numerator is the number of moles of that solute. But again, if you took all of the solutes out and you just left with the pure solvent, the difference in the volume is going to be tiny, down to the fourth, fifth, sixth decimal place, and we usually don't need to report to that precision in most circumstances. Okay, the next thing to note is that, so if we're dissolving NaCl in the solution in water, well, we know that the NaCl is going to break up into Na plus and Cl minus ions, right? So doesn't this perhaps come into play in terms of molarity, right? We need to count. We've got this many particles. It's however much NaCl we dissolve times 2. It's that many moles of particles per liter of solution. No. You look at it like how many moles of the substance before you added it into the solution. How many moles did you have? You weighed out a precise mass of NaCl. So you can use the molar mass to get the number of moles. That's what goes here. It doesn't matter. You don't think about what happens after you dissolve what you've weighed out into the solution. Now, but you have the option to do that, though. Like you could view it from the perspective of after a certain substance has broken up into the solution. But in that case, you would say, okay, if we dissolved 2 moles of NaCl into the solution, well, then if we could, the molarity of the solution would be 2 divided by the volume of the solution, the molarity of NaCl. But you could also say that the molarity in the resulting solution, the molarity of Na plus ions is 2 moles divided by the volume of the solution. Or the molarity of Cl minus ions there's going to be 2 moles of Cl minus ions, right? Or you could say the molarity of ions in the resulting solution would be 4. There's 4 moles of ions per divided by the volume of the solution, right? It's really what it comes down to what in this, for the moles here, you could put a subscript. If you say NaCl, then okay, how many of these NaCl units were dissolved? It doesn't matter if they break up, whatever they do in the solution doesn't matter. How many of these were dissolved per volume in liters of the solution? Or you could say like that, right? Or just how many moles of ions? Okay, now why is molarity a convenient concentration unit in chemistry? Well, okay, because it directly relates the moles of a substance to the final volume of the solution. And this is useful for, in particular, stoichiometry, right? We have that mole information. Okay, but then it's not just the mole information. We also have the volume of the solution information mixed in as well, right? We can see a chemical equation taking place in solution. And with concentration, we've got the mole information and the volume of solution information. Describe the steps involved in preparing a solution of known molar concentration using a volumetric flask. Okay, so molar concentration is another term for molarity. If someone says it refers to the molar concentration of a certain solute in the solution, they're referring to molarity, which makes sense because it's the concentration that's giving you with the amount being moles. Okay, and they're asking here if we wanted to, let's say we wanted to prepare an aqueous solution of silver nitrate with a specific molarity. That solution has a specific molarity of silver nitrate. Right, so here's silver nitrate. Okay, well, what we would do is we would weigh out. So, okay, we know what, coming into this, we know what the desired concentration of the molarity of our solution, the molarity of silver nitrate, needs to be. We're choosing this, right? We want this molarity of a silver nitrate aqueous solution, but then we also know what we want the volume, the final volume of the solution to be, right? We're specifying this. Okay, well, with that then, since we know the final volume that we want, then, so we're specifying a concentration. We specify the molarity. Okay, then we know what the final volume of the solution is going to be. And so we can just multiply that molarity by the volume and just convert that volume to liters. And what we'll get is the number of moles of silver nitrate. Okay, then with the number of moles, we can take the formula weight of AgNO3, get the corresponding grams of AgNO3 and then precisely weigh out that much solid AgNO3, right? So then what we do next is we get a volumetric flask and put a marker showing that final volume of solution, okay? And then before you start pouring any liquid, you just put that mass of AgNO3 into the flask, okay? Then you just add a little bit of water to that solid powder. Not a lot, just enough to where you just submerge the powder. Then you start sloshing it around and let it dissolve. Maybe you add a little bit more and you really slosh it around, let it dissolve. Keep adding more water, sloshing it around, let it dissolve until you fully dissolve all of that silver nitrate. Once it's all dissolved, then you just add additional water until the volume of the solution is at the marker. Describe how you would prepare 250 milliliters of a 0.707 molarity sodium nitrate solution. Okay, so this is exactly what we just talked about, but now we're going to look at a specific example. So we've specified that we want a concentration of 0.707 molarity, and then now remember, any concentration is relative to a specific solute. So it's technically you're with molarity, you're always putting a subscript. Molarity technically doesn't make sense without a subscript like this. Molarity of what? So the concentration of 0.707 molarity of sodium nitrate. Okay, now we've got also what's going to need a subscript is you have the number of moles of that solute. Now, the volume of the solution doesn't need a subscript. I mean, perhaps maybe you could say it does in that you'd put what the solvent is, but really technically it doesn't. So, okay, what's the final volume of the solution? 250 milliliters. Okay, but molarity is moles per liter. So we need to convert this to liters to make sure the units, when we specify a molarity, the units of molarity are moles per liter. So this 0.707 is moles per liter. So you have the moles of sodium nitrate, and now that's per, and you divide that by 0.250. Okay, so cross multiplying 0.707 times 0.250, 0.17675. Moles of sodium nitrate must be in this solution here. Okay, but now they're asking us, how are we going to prepare this solution? Well, we don't directly measure out moles of substances. We convert moles to grams, and we directly measure, our instruments are in grams. So, okay, how do we convert this many moles of sodium nitrate to grams? Well, we just use the formula weight, right? The formula weight, the molar mass, the molecular weight. Formula weight is just the term for the molar mass of a compound that's not a molecule. So, okay, what is the molar mass or the formula weight of sodium nitrate? Okay, sodium atomic weight, 22.990. Okay, nitrogen atomic weight, 14.007. Atomic weight or molar mass is the same quantity, right? Now, oxygen, 15.999. Okay, adding all of this up. Got $84.994. That's grams of NaNO3 per mole of NaNO3. You don't have to write out the units this explicitly all the time, but when you're trying to practice and understand the meaning of these problems in chemistry or any subject, this is really helpful to be explicit and detailed about everything you're doing. This is exactly what this means here. 84.994. For every, you have 84.994 grams of sodium nitrate for every mole, 1 mole of sodium nitrate. If you have 1 mole, a count of a mole of these, 6.022 times 10 to the 23rd of these, then the mass of that in grams is going to be this. Okay, so we've got 0.17675 moles of NaNO3. And now, but we know that for every 1 mole of NaNO3, there's 84.994 grams of NaNO3. So 15.023. Okay, so now to make this solution, to prepare this solution, we would weigh out this many grams of, here's sodium nitrate, then get a volumetric flask, put a marker at 250 milliliters, put the sodium nitrate into the flask, add a little bit of water, start sloshing it around, add a little bit of more water, slosh the solution around until you get all of that solid dissolved, then just add whatever remaining water you need up to the marker. How many grams of potassium hydroxide are present in 35 milliliters of a 5.5 molarity solution? Okay, so we've got the concentration of this solution is 5.5 molarity. 5.5 molarity of what? Of potassium hydroxide. Okay, so that means that there's, in this solution, you've got a certain number of moles of potassium hydroxide per liter of this solution. So how many liters here in the equation? Okay, the solution, it tells us, is the total volume is 35 milliliters. So molarity is in units of liters, so we need to put 0.035. Okay, so 5.5 times 0.035, 0.1925. There must be if this solution, if this is the concentration and this is the volume of solution, then this concentration is relative to potassium hydroxide, then it must be the case that there's 0.1925 moles of potassium hydroxide in the solution. Yes, this dissociates into K plus and OH minus ions, but that's not what we're referring to here. This 5.5 molarity was in reference to KOH. So, okay. But they're asking, okay, well, how many grams is this? Well, that's easy. What's the molar mass of potassium hydroxide? Okay, atomic weight of potassium is 39.098. Oxygen is 15.999. And hydrogen is 1.008. Okay, so 39.098. Formula weight is 56.105, so there's 56.105 grams of potassium hydroxide per mole. Okay, so then if we've got 0.1925 moles of potassium hydroxide, then since we know that there's, for every 1 mole of potassium hydroxide, there's 56.105 grams of potassium hydroxide, then that means there must be, in 0.1925 moles, that must, the mass of that must be 10.8. In a 5.5 molarity solution of potassium hydroxide, to where the total volume of this solution is 35 milliliters, there must be 10.8 grams of potassium hydroxide dissolved in that solution. calculate the molarity of each of the following solutions. So first, part A, 6.57 grams of methanol in 150 milliliters of solution. Okay, so what is the formula weight of methanol? Okay, well, for the rest of this video, I'll go ahead and just do a Google search for formula weights, which you can do. Just be careful. Google is not as reliable of a source as, say, a peer-reviewed scientific publication, but even scientific publications aren't bulletproof reliable either, so it's really up to you to filter out where exactly you're getting your information. For example, your intuition should tell you that a very reliable source of information, scientific information, would be a textbook, but not just any textbook, a textbook that is widely used in, let's say, multiple countries, right? Because in that case, if there was errors, people would find them. If there was errors or inconsistencies, they would be found. Okay, but if you're doing a Google search for the formula weight of methanol, you get 32.04 grams per mole. Okay, so if we have 6.57 grams of methanol, and we know that there's 32.04 grams of methanol for every 1 mole of methanol, then this must be 0.2051 moles of methanol. Okay, so we've got this many moles of methanol in solution, which is useful if we're trying to calculate the concentration in molarity, right, of a certain substance. We need to know, okay, well then how many moles are dissolved? Well, here's how many moles are dissolved. Okay, but now in how much liters of solution are these moles dissolved? Well, it tells us 150 milliliters. But molarity of CH3OH, so this is kind of confusing, the molar mass, you can also use a capital M, so, but here, okay, this is molarity, so the concentration in molarity of methanol is, you have 0.2051 moles, but it's per how many liters of solution, not milliliters. So 150 milliliters in liters is 0.150. So 1.37. Molarity of methanol is the concentration of the solution in part A. Okay, part B. So I'll say what is the formula weight of calcium chloride? That's 110.98 grams of calcium chloride per mole. So, okay, if we've got 10.4 grams of calcium chloride in this solution, then how many moles is that? Well, there's 110.98 grams of calcium chloride for every mole. So, .0937. Okay, so the molarity of calcium chloride in this solution is the number of moles of calcium chloride dissolved, which we just determined as 0.0937, divided by the volume of solution in liters. Well, it gives us the volume of solution in milliliters, 228 milliliters. That's 0.220 liters. So this divided by 0.220, 0.426 molarity. Molarity of what? Calcium chloride. as the concentration of calcium chloride. Okay, part C, what is the concentration of you have a solution that contains 7.82 grams of naphthalene dissolved, and the entire volume of that solution, this is not an aqueous solution, this is a benzene solution, naphthalene dissolved in benzene, and the entire volume of the solution is 85.2 milliliters. What's the concentration of naphthalene in this solution? And in molarity, calculate the molarity. And so, yeah, we can do this. This isn't an aqueous solution, but concentration, the idea of concentration and molarity is relative to any solution. But here we're talking about, in this chapter, we're talking about aqueous solutions, but the textbook mentioned that we can think about molarity at the moment relative to solutes dissolved in any liquid solvent. So we've got the volume of the liquid solvent relative to liters. Okay, so what is the formula weight of naphthalene? Doing a Google search, you get 128.17 grams per mole. So how many moles if we have 7.82 grams of naphthalene, how many moles is this? Okay. .0610. Okay, so the molarity of this solution, concentration of naphthalene, we've got 0.0610 moles, and there's the liters of solution is 0.0852. .716. Okay, determine how many grams of each of the following solutes would be needed to make 250 milliliters of a 0.1 molarity solution. So, okay, part A, if we had a 0.1 molarity solution of cesium iodide, and we knew that the total volume of that solution was 250 milliliters, then how many grams of cesium iodide must be dissolved? Well, okay, let's just get the formula weight of cesium iodide. Doing a Google search, you get that the formula weight is 259.81 grams per mole. Okay, now, so okay, we've got a 0.10 molarity solution. Molarity of cesium iodide. So we know that that means that there's N moles of cesium iodide per liter of solution, and it gives us it's 0.250 liters of solution. Okay, so we can get the number of moles. We can use the formula for molarity to get the number of moles of cesium iodide dissolved. So 0.1 times 0.25, 0.025. Okay, so now we just need to convert this to grams. We have the amount of cesium iodide dissolved. We got it, but it's just in the units of moles. We just need to convert this to grams. So how many grams, if you have 0.025 moles of cesium iodide, how many grams is that? Well, we know that there's 259.81 grams of cesium iodide for every 1 mole. Cesium iodide. 6.5. Okay, what about part B, sulfuric acid? So the formula weight of sulfuric acid is 98.08 grams per mole. Okay, so we've got a So every one of these solutions is going to have a 0.1 molarity concentration of the solute in this volume. So we can just, instead of rewriting this formula every time, we just know that we're going to have 0.1 molarity of the solute is equal to the number of moles of the solute per, and then 0.25. Okay, so then that means that the number of moles of H2SO4 and the part B solution is we just do 0.25 times 0.1. The number, okay, yeah, the number of moles is going to be exactly the same. For every one of these solutions, the number of moles, since the concentration is fixed and the volume of solution is fixed, then the number of moles of each of these solutes is fixed. 0.025 in X, whatever the solute is 0.025 moles. So to answer each one of these, all we need to do is just multiply 0.025 by the formula weight, right? Because, okay, we get to this point, we've got in moles of whatever the solute, which is 0.025. So we've got 0.025 moles of the solute. And then the formula weight is just, okay, you've got this many grams of the solute for every 1 mole of the solute. And that's the answer. So, okay, what's 0.025 times 98.08? 2.452. Okay, that's part B. Part C. So, okay, what is the formula weight of sodium carbonate? Do a Google search, you get 105.99. Okay, so 0.025 times 2.65 grams of sodium carbonate. Okay, potassium dichromate. Formula weight is 294.18. So 294.18 times 0.025, 7.35. Okay, part E, potassium permanganate. The formula weight is 158.03 grams per mole, so 158.03 times 0.025, 3.95 grams. Barium hydroxide, often used to titrate weak organic acids, is obtained as the octahydrate BaOH2 with 8 water molecules attached. What mass of this barium hydroxide hydrate, octahydrate, would be required to make 500 milliliters of a solution that is 0.15 molarity in hydroxide ions? So they're asking about this molarity here, right? It's really important when you're specifying a concentration, you're really needing to be specific about concentration of what. They're not saying that this 0.15 molarity is the molarity of this barium hydroxide octahydrate. They're saying that what's the concentration of this solution in terms of OH minus ions, the concentration of OH minus ions in the solution. Well, they're telling us that they're saying, okay, if you're going to have this concentration of hydroxide ions, then what would you need to, and they're telling us the final volume of the solution, then what does that correspond to in terms of the amount of this barium hydroxide octahydrate dissolved? So, okay, let's just start with, we're given the molarity of hydroxide ions, and we know the formula for molarity means that this is going to be a certain number of moles of hydroxide ions per volume of the entire solution. the volume of the solution in liters. So they're giving us the final volume of the solution is 500 milliliters, but molarity is in liters, so we put 0.5. Okay, so we can get some information here because we've got the concentration, the number of moles of hydroxide ions in the solution must be 0.5 times 0.15, 0.075. Okay, so now we just need to think about, so what happens when you dissolve this barium hydroxide octahydrate in water? Well, okay, barium hydroxide, BaOH2, that's an ionic compound, and if we come to the solubility rules for these different ionic compounds at room temperature, all of this, they haven't stated some other temperature other than room temperature. So we're assuming all of this is at room temperature, 25 degrees Celsius. So, okay, if you've got hydroxides are going to be insoluble, but barium is an exception. If barium 2+ is the cation. So this is soluble, so this dissolves and dissociates into Ba2+ and OH- ions. But then we also have to consider that it's 2 OH- ions for every one of these entire barium hydroxide octahydrates dissolved. Okay, but then as far as the attached 8 water molecules, well, those just kind of get mixed into the solution, right? Like once, if you're dissolved in, remember, if you're dissolved in water or dissolved in any, you can think about just like a liquid solvent, then you're just attached to at all sides, completely surrounded and attached to the solvent molecules. You're completely hydrated in the case of an aqueous solution. So this 8H2O just effectively gets just mixed in with the rest of the water. And you're just left with dissolved or fully hydrated Ba2+ ions and OH- ions. Okay, but now it's asking us for the mass of this barium hydroxide octahydrate that you need to dissolve to get a concentration of 0.075 molarity hydroxide ions. We still need to consider this as far as the mass of this compound that's being dissolved, because you could think about it's like to prepare a solution like this from a substance with this chemical formula, you're going to be weighing out, for each unit here, you're also going to be weighing out 8 water molecules. Even though these 8 water molecules disappear into the aqueous solution, still when you're initially preparing the solute to dissolve, you're weighing out all of this. And so, okay, what we need to do is we can start with the 0.075 moles of OH-. Okay, and all we're trying to do is see how many moles, and then convert that to grams of this barium hydroxide octahydrate contain this many moles of just a single OH-, a single OH group. So, okay, in terms of moles, well, we've got for every one of these, actually just one itself, or you could say 1 mole, same idea, right? A mole is just a scalar that you apply to a count. So for every one of these or 1 mole of these, how many OHs are there? Well, there's 2, right? So there's 2 moles of OH- for every 1 mole of right? And now also remember when you see, you see an ion like this, and you start to think, well, there's an extra electron floating around somewhere, or an extra maybe 2 or 3 electrons that are, how are we accounting for those with these mass measurements? Well, remember, like a single electron or 2 or 3 or 4 electrons, whatever, in terms of mass is completely negligible. So we don't care about, we're not accounting for that extra electron that came off from somewhere to go to this OH group. Okay? So if you've got 0.075 moles of OH- ions, then in terms of barium hydroxide octahydrate, that means you must have 0.075 divided by 2 moles of barium hydroxide octahydrate, right? So there you go. If we dissolved 0.075 divided by 2 moles of barium hydroxide octahydrate, in 500 milliliters of water, then the resulting concentration of OH minus ions would be this. But now they're asking us not for the moles of barium hydroxide octahydrate, but the mass. What is this amount in terms of grams? Okay, well, you just use the formula weight here. So I'll Google the formula weight for barium hydroxide octahydrate is 315.46 grams for every 1 mole. And there you go. So, okay, it was 0.075 times 315.46 divided by 2. 11.8.